coordinate. Does that change my evaluation of the Laplace? And the answer is no. Okay, that's again the essence, okay, the essence of that Laplace will stay invariant under rigid motions. Okay, under rigid motions. How do we prove that? How do we prove that? Well, first of all, for spatial translation. Okay? For spatial translation, that simply means that I'm choosing another coordinate, such as x prime equals to x plus a, and y prime equals to y plus b. Right? X prime equals to x plus a, and y prime equals to y plus b. Well, what can you say? What can you say about u x prime plus u y prime y prime? What can you say about u x prime plus u y prime y prime? Well, first of all, what is the relation between ux prime and ux? What is the relation between ux prime and ux? They are the same thing, right? They are the same thing. They are the same thing. So is it good? Okay, they are the same thing. So first order differentiation is spatially translationally invariant. They are the same thing. Okay, and therefore ux prime x prime equals to ux x. If you don't believe it, okay, you can. If you can take the bother, then just you can go through the chain rule of the differentiation, and then you can find the answer. Okay? It's the same thing. Well, but the problematic part, the non-trivial part, is the rotation. Okay, the non-trivial part is the rotation. If I am having a, let's say, I'm having a vector, okay? I'm having a vector, let's say, this is my x, y. If I'm having, let's say x0, y0, okay? x0, y0. How do I rotate this vector? How do I rotate this vector counterclockwise for theta degree? How do I rotate this vector counterclockwise for theta degree under using a 2x2 matrix, using the linear mapping? How do I do that? It's a linear mapping, right? This is of course a linear mapping. So that is actually what we find is that is actually okay, and actually so that is actually, let's say, x0 prime, y0 prime. This is after the rotation. Okay, that actually equals to a linear mapping. Okay, multiplied with x0 and y0. Of course, this is because rotation is linear. Okay, rotation is linear. So we can do that using a 2x2 matrix. And this 2x2 matrix is exactly cosine theta, sine theta, and negative sine theta, and cosine theta. Okay, so this is how you can rotate. Okay, this is how you can rotate from x0, y0 to x0 to x0 prime and y0 prime. Like that. This is the linear mapping that you need. Okay, this is the linear mapping that you need. So what we are going to prove is that even under the rotation, okay, then the Laplace will still stay invariant. So now let's say I'm having my x prime, y prime, okay, x prime, y prime, this guy equals to, okay, x, y, okay, this is the new coordinate, cosine theta, and sine theta, and negative sine theta, and then cosine theta. Okay, this is the rotation. Well, this is my rotation, right? Okay, so if I write down everything, open the bracket, then I'm going to have x prime equals to x cosine theta, and then plus y sine theta. And then y prime, which equals to negative x sine theta, and then plus y cosine theta. Okay? Well, if you would like to verify, okay, the invariance, then we will be first looking into how do we express ux, okay, into ux prime and uy prime. How do we express how do we express uy into ux prime and uy prime? Okay, and then how do we express uxx and uyy, okay, into ux prime and uy prime? Okay. Let me first write down the first two terms. My ux actually equals to cosine theta ux prime, and then minus sine theta uy prime. My uy actually equals to sine theta ux prime, and then plus cosine theta uy prime. Okay, and the uxx and the uyy, okay, will actually be more fuzzy than this. Okay, and you can refer to the page number 156. Okay, for this. Okay, and then finally, you will be seeing that ux prime x prime plus uy prime y prime exactly equals to uxx plus uy. Okay, this is something that can be verified by the chain rule, but it probably doesn't worth us to spend too much time on this. Okay. So this is the rotational. This is the so-called the rotational invariance. Okay. So this is the rotational invariance. Okay. And so when we are talking about the rotational invariance, okay, so this actually suggests that if we could write the Laplace operator, okay, into the polar coordinate, actually the corresponding form should be extremely simple. Okay, so the next question is that how to write Laplace, okay, which equals to partial x squared and then plus partial y squared, okay, into polar coordinate. Okay, because again, what is the motivation? What is the motivation? You see, we have really proved the rotational invariance, right? We have really proved that the Laplace, okay, it actually has exactly the same form. It has exactly the same form when we are rotating the coordinate, right? So this actually suggests that my Laplace is going to have an extremely simple form. Okay, my Laplace is going to have an extremely simple form when we are using the polar coordinate, okay, to represent everything. Again, what is a polar coordinate? Polar coordinate means that my x is written into r cosine theta, and my y is something like r sine theta. So again, this is my x and y. Okay, this is my x and y. So polar coordinate means that this is the original point. R means how far away it is away from the original point, and theta is that what is the angle? Okay, what is the angle between the vector x, y, and the 0 degree? Okay. So of course, one thing that we should mention right away. Okay, that what is the domain? What is the domain of r and theta? What is the domain of r and theta? Can r be negative? R cannot be negative. R is between 0 to infinity. Well, actually, including 0 to infinity. So which means that when r is 0, it doesn't really matter what theta is. Okay. And what is the space for my theta?
From 0 to 2.
From 0 to 2 pi. Okay, this is part of the answer. But what can I say about the 2 pi? 2 pi means that the angle has already gone for a complete circle. Going back here, right? So in this case, my 2 pi should be what? Should be exactly the same as 0. Okay, so which means that my theta is actually in a periodic space. Okay, it's actually in a periodic space. For this type of periodic space, we express it as okay, a t 0 2 pi. Okay, this is which means that my theta, okay, my theta is in a periodic space. Okay, so what is this? What does this remind you? What does this remind you of chapter 5? Okay, periodic boundary condition, right? Periodic boundary condition. So that means that for any function, okay, for any function that's only about theta, it's going to be a what kind of function? Periodic function. It's going to be a periodic function, and the period will be exactly 2 pi. So it's good, okay? And a little bit spoiler over here is that in chapter 2 and chapter 3, actually especially in chapter 3, that means that we will be looking into the full Fourier series for this type of the periodic, for this type of periodic functions. Okay, especially when we are looking into a boundary condition, okay, a boundary condition as a circle. Okay, a boundary condition as a circle. So now, our goal is to write the Laplace, okay, into the polar coordinate. Our goal is to write the Laplace into the polar coordinate. So that means that we will be first looking into, what is partial, okay, well, so what is partial, let's say, partial u, how do we write partial u, partial x, partial u, partial y, okay, into partial u, partial theta, and partial u, partial r. Okay, we'll be needing this. Well, that means that we will be looking into the Jacobian. Okay, we'll be looking into the Jacobian. Okay, the Jacobian, let's say the Jacobian matrix. Okay, the Jacobian matrix. Let's say partial x y to partial r theta. Okay, this is written into. This is actually a matrix containing partial x, partial r, and partial y, partial r, and partial x, partial theta, and partial y, partial theta. Can you please tell me what is that? What is partial x, partial r? What is partial y, partial r? What is partial x, partial theta? And what is partial y, partial theta? What is that?
Cosine theta, sine theta.
Okay, partial x, partial r are according to the formula between x, y, r, theta. That should be. What is partial x, partial r? Cosine theta. What is partial y, partial r? Sine theta. What is partial x, partial theta? Okay, negative r sine theta. Okay, what is partial y, partial theta? R cosine theta. Okay, this is very straightforward. But you see, in order, because what we are having is the partial x. Okay, because we will be starting from uxx plus uyy. Okay, two things including like urr, u theta, this kind of things. We don't know what combination is that. Right? We'll be starting from this to this. Therefore, if we want to use the chain rule, okay, actually we need to look into things like partial r, partial x, okay, and partial theta, partial x, and partial r, partial y, partial theta, partial y. Right? We actually need that to fulfill our chain rule. So, but luckily, we know that, okay, this is actually going to be the inverse Jacobian. Okay, this is actually going to be the inverse Jacobian. This is partial r theta, partial x y. Okay, this is actually the inverse Jacobian. Okay, this is actually the inverse. Okay, the inverse of partial x y and partial r theta. Okay, which means that we only need to take the inverse. Okay, we only need to take the inverse to obtain this inverse Jacobian. Okay, we only need to take the inverse. Well, if I wanted to take an inverse, that means that, okay, this guy multiplied by a A, B, C, D should equals to what? Should equals to what? If I'm looking into the inverse, let's say this is my A, B, C, D. A, B, C, D.
Oh,
So this guy's inverse.
1, 1, 1.
1, 0, 0, 1, right? Inverse. 1, 0, 0, 1. So that's good. So that tells me that this guy multiplied by this guy is what? Is 1. So that's basically speaking that cosine theta, A cosine theta plus C sine theta equals to 1, right? So what do you want to assign? Because you see, this has to be true for any choice. This has to be true for any choice of theta, right? So what do you want to assign for A and C? What do you want to assign for A and C? I just want to assign A as a cosine, okay, and C as a sine, right? Because this is the easiest way out. This seems to be the easiest way out. So let's try it. Okay, so let's try it. So now let's say this guy. Okay, this guy is my cosine theta. This guy is my sine theta. So that's good. Okay, and well, the other way we can verify if our choice is valid is that now what is this multiplied by this? The second row and first column, this should be 0, right? This row multiplied by this column is going to be 0, right? So what is that? That's negative r sine theta multiplied by cosine theta. Here, r cosine theta multiplied by sine theta. Indeed, it cancels. So this actually suggests that our choice is very good. Okay, our choice is very good. So likewise, using the similar method, we'll be able to show that we'll be able to prove that this guy is actually cosine theta, sine theta, and then negative sine theta over r and cosine theta over r. Okay? This is the inverse Jacobian. Therefore, according to the chain rule, my partial x, that should equals to what? That should equals to what? Let's say, okay, my partial u partial x. That should equals to, okay, my partial x, that's actually my partial u partial r, okay, and then multiplied by partial r partial x, right? And then plus my partial u partial theta multiplied by partial theta partial x. See, both of these terms, partial r partial x, partial theta partial x, is here. It's in the inverse Jacobian, not in the direct Jacobian. That's why we need to compute the inverse Jacobian, right? Okay. So, according to the inverse Jacobian, it tells us that this equals to cosine theta, partial u, partial r, and then minus sine theta over r, okay, and then partial u, partial theta. Yes. So we're good? Same reason. My partial u, partial y, that should equals to sine theta, partial u, partial r, and then plus, okay, cosine theta over r, partial u, partial theta. Okay, this is my part. This is how I can express my partial u, partial x, partial u, partial y into partial u, partial r, and partial u, partial theta. Okay. Now, what can I say about my partial u, the second order derivative of partial u, the second order derivative of partial x? Sorry. What can I say about my uxx and uyy? What can I say about that? So why don't we use about 5 minutes to do the computation by yourself? Okay, so you can have a better impression of this. know some of you want to go directly to the book for the answer. And what I suggest is that really doing that computation using about 3 to 5 minutes is not going to cost your life, and it will really make your impression much deeper, especially when you're in a class.
他到底是什么情况？哎，
So is there anyone have any question about the first step?
就你
It's just that because uxx is the first order derivative of some of ux, right? So you just need to replace the u to the ux to finish the first step, right? And then the next step would simply be replacing the ux again by this formula. Then you will be obtaining the answer, right? Okay. So sorry for spoiling everything, but we do have to move on. So now we can see that this guy is indeed, so again, what is ux? Ux is now, okay, so this cosine theta and then partial ux is exactly, okay, cosine theta ur, okay, and then minus sine theta over r, and then u theta, okay, partial r. And then plus, sorry, it's actually not plus, actually minus cosine theta over r. So minus cosine theta over r. Minus sine theta over r, sorry. Minus sine theta over r. Yes, okay, and then plus, here it should be minus. Minus sine theta over r, and then partial theta. So in the bracket, it's going to be cosine theta ur minus sine theta over r u theta. It's going to be something like this. And the rest of it, and then the rest of it is going to work out all the derivatives. Okay, it's going to be working out all the derivatives. let's do this for once. Okay, let's do this together for once. Okay, and then we'll be avoiding doing the second one because the second one is going to be exactly the same. So this guy is actually, so first of all, we will be taking the partial derivative of everything inside, okay, to R. So the first thing, what is the first term partial and partial R? Cosine, what is the first order derivative? Well, first order derivative of what's R of cosine theta u R?
Oh,
Cosine theta will stay, right? And then u R, right? Okay. And cosine theta, with the cosine theta, the existing cosine theta that we have, is going to be cosine squared theta, and then u R R. So this is the first term. What about the second term? What about the second term? It's going to be cosine theta, sine theta, u theta. These things has nothing to do with R, right? Okay, sorry, u theta and dr and partial R is going to be a u theta R or u R theta. It doesn't really matter. But here is actually a 1 over R, right? Here is actually a 1 over R. So actually there will be two terms coming out. Okay, there will be two terms coming out. The first term is going to be, okay, cosine theta and then sine theta over R squared and then u theta. Okay? Okay, and then minus cosine theta, sine theta over R, u theta R. Sounds good? Don't forget, okay, sine theta, it has nothing to do with the R, right? But R, 1 over R, is a function of R. U theta is also a function of R. Okay, so the rules of the product rule. Okay, just simply using the product. Okay, and here, negative sine theta over R. What about the first term? Okay, what about the first term? What about the first term? The first term, cosine theta, UR, partial R. So again, these two things, okay, both of these two things are something about theta. So again, product, okay? We need again a product. So minus sine theta over R, okay, and then multiply by, the first thing is that negative sine theta UR, and then plus, okay, and then plus cosine theta UR theta, or U theta R, doesn't really matter. Okay, so this is the first thing. And then the second thing, okay, sine theta over R, U theta. Again, sine theta is something about theta. U theta is also something about theta. So it's going to be, okay, it's going to be negative, okay, cosine theta over R, U theta. And then minus sine theta over R, U theta, theta. Okay, you just need to work out all the sums. Okay, you just need to work out all the sums, and then finally you will be having cosine squared theta. Okay, cosine squared theta, and then URR minus 2 sine. Okay, minus 2 sine theta, cosine theta over R. Okay, and then UR theta, and then plus sine squared theta over R squared. Okay, U theta theta, and then plus 2 sine theta cosine theta. Okay, R squared U theta, and then finally plus sine squared theta over R UR. I admit that I was simply going to be copying everything from the book. Okay, okay, especially except for the first step. Okay, I was computing it by myself. Okay, but the final answer was that I copied from the book. Okay, so this, don't forget, this is my partial u partial x. This is the u-axis. Okay, this is how u-axis is expressed in the derivatives of the polar coordinates. And UYY, okay, UYY, what you're going to find is something that is extremely similar. And I'm going to directly write down the answer. It's going to be actually sine theta, sine squared theta, URR, okay? And then plus 2 sine theta, cosine theta over R, UR theta. And then plus, okay, cosine squared theta over r squared u theta, and then minus 2 sine theta cosine theta, okay, r squared u theta, and then finally plus cosine squared theta over r u r. Okay? Don't forget, our goal is to summing these two things up. Okay, our goal is to sum these two things up. So, okay, finally the exciting moment will come. Okay, so now we need to sum up
R's.
these 10 terms. Okay, we need to sum up these 10 terms, and you might have a question: is that am I insane to show you all this process? Right? Actually, what we find is surprisingly cancellations. Okay, surprising cancellations. Let's see the first term. U R R. Cosine theta plus sine theta. What do we get? One. So we are going to have 1 U R R. Second term, minus 2 sine theta cosine theta over r u r theta. Plus 2 sine theta cosine theta over r u r theta. We get 0. Cancels everything. The third term, sine theta over r squared u theta theta. Cosine squared theta r over r squared u theta theta. We will be obtaining 1 over r squared u theta theta. Okay. Fourth term, plus 2 sine cosine over r u theta. R squared u theta. Minus 2 sine cosine over r squared u theta. Cancels. Last term, sine theta over r u r. Cosine theta over r u r will be obtained 1 over r. Okay. So finally we have that okay, again, the Laplace u, which equals to uxx plus uyy under the polar coordinate, it has an extremely simple, okay, well, not extremely simple, but actually related simple one, which is actually urr plus 1 over r ur, and then plus 1 over r squared u theta. Okay, 1 over square u theta. So good? Okay, so this is how the Laplace this is how the 2D Laplace, okay, 2D Laplace is represented in the polar coordinate. Okay, this is how the 2D Laplace is represented in the polar coordinate. Okay, then probably the suitable one last question, okay, for this class is that since we are already representing everything in a polar coordinate, can we use this? Okay, can we use this formula of the Laplace, okay, expressed in the polar coordinate to obtain all the possible harmonic functions that are rotationally invariant? Can we use this guy, okay, to obtain all the harmonic functions that are rotationally invariant? Which means that, okay, so suppose that I'm having a 2D function. Okay, suppose that this is my x, this is my y. Okay, suppose that I'm having a harmonic function. Okay, and I am turning. So let's say I'm having this. Okay, and it seems that I'm only able to move it up and down. But I'm unable to rotate it. Okay, but suppose that I am rotating this harmonic function. Okay, but after rotation, it's going to be the same thing. Okay, can we use this polar coordinate, the Laplacian, okay, under this polar coordinate to obtain all the harmonic functions that are rotationally invariant? So first of all, there are two requirements, right? It has to be a harmonic function, and secondly, it should be rotationally invariant. First of all, what does it mean that it is a harmonic function? Okay, so that means that my Laplace u equals to 0, right? And more specific, that means that under the polar coordinate, that means that my urr plus 1 over r ur, okay, and then plus 1 over r squared u theta. This guy is 0. This is okay, right? This is the very direct definition of a harmonic function. What does it mean that my u is rotationally invariant? What does it mean that my u is rotationally invariant? What does that mean? So in this case, can my u still contain the variable theta? If u is rotationally invariant, that means what? If u is rotationally invariant, that means that, okay, my u r0, okay, should equals to what? Should equals to u r, let's say, 30 degree, okay? And should also equals to u r, okay, 90 degree. Then equals to u r any degree, right? Say that. Is that right? Is that right? If that's rotationally invariant, something is rotationally. So what kind of things is rotationally invariant? This guy is rotationally invariant. See? This guy is rotationally invariant. In that case, okay, this, if I'm taking this angle, the function, consider that this bottle, okay, the shape of this bottle is exactly my 2D function, okay, and this is the third dimension. That means that this angle, okay, this angle, the function on this angle should be exactly the same as the function on this angle. This means rotationally invariant, right? This means rotationally invariant. Well, ignore this kind of things, okay, but this is rotationally invariant. Okay, rotational. So again, rotationally invariant means that, okay, rotationally invariant means that, okay, so here, okay, means what? Rotationally invariant means that on this circle it's a constant. On this circle is also a constant. On this circle is also a constant. So far so good? So far so good? Okay. Constant. So this is C1, C2, C3. So that means that my u r theta is actually a u r. It's only a function of r. So what can I say? What can I say for such a function about u theta theta? If it's a constant function for any angle, then what can I say about u theta theta? 0. Right? Then 0. So that means that my u theta, because now my function u is only a function of r, so u theta is of course 0. So that means that u r plus 1 over r u r equals to 0. Okay, can you solve this equation? So this is the last class of the class of this lecture. Can you solve this equation? Can you solve this equation? This is actually 1D ODE. Can you solve this equation? Go ahead, come on. Use your pen. Of course, this will, you can start from what? You can start from, let's say, u r equals to v, right? So this is actually v r plus 1 over r v equals to 0. Okay, so this means that, okay, this simply means that, okay, so that this simply means that my RV, the first order derivative RV, this guy is 0. Okay, how can you see that? You can simply modify R on both sides. Okay, modify R on both sides and then take the differentiation. This is going to give you, okay, RVR, okay, and V, RVR plus V equals to 0, then you divide by R, you're going to get this. So that simply means that my RV is a constant. My RV is a constant. Let's say it's constant C1. Okay, C1. But don't forget my V is so that means that my V equals to C1 over R. But don't forget that actually my V is actually UR equals to C1 over R. And you need to integrate it for one more time. Okay, you integrate it for one more time. So what is my u? What is my u? My u should be c1. Okay, so what is the integration of 1 over
2括2 有
r?
r 到，
What is the integration of 1 over r?
好快啊！
What is the
用
integration
快
of 1
好
over
多
r? Log r, right? Okay. Log r is actually log, okay, log r, and then plus c2 come from the integration. Okay, here is the most exciting part. What kind of function is this? What kind of function is it? Is this a smooth function or analytical function everywhere?
It's
Where is the problem? Where's the problem? Where is it problematic? when r is 0,
equals
right?
to 0.
So what is the so again, don't forget what's u, what we computed from u. We were computing u as the harmonic function that's rotationally invariant, right? That is rotationally invariant. But finally, what we got, and we started from what? We started from assuming that Laplace u is 0 everywhere. But by solving that, we obtain something that's definitely, you see, since my ur, okay, since my ur is actually infinity, it goes to actually negative, goes to negative infinity at the original point. The Laplace of ur, not to say, it doesn't even exist at 0. Right? Why is that? Why is that? What incurred this contradiction?
Radius is 0 can't be invariant.
Sorry?
If the radius is 0.
That's actually this actually part of the core idea. So first of all, under the polar coordinate, okay, the original point is always specifically guiltless. Okay, because for the polar coordinate, in the polar coordinate, when I'm taking my r equals to 0, okay, then it doesn't really matter what zeta is, right? It is all going to be the same point. This is the first thing. And the second thing is that, you see, what did I tell you about this? I said that, okay, for a rotationally invariant harmonic function, okay, I'm drawing a circle, then it has to be a constant, right? I'm drawing a circle, it has to be a constant. I'm drawing a circle, it has to be a constant. This is what I said, right? But using the maximum principle, this part doesn't belong to you, but using the, what can you obtain using the maximum principle? If I am saying that, okay, now I have a harmonic function which is everywhere in this small circle, defined everywhere in this small circle, and it is also a constant on the boundary. What can you say?
Oh,
Then it has to be what? There's only one possibility for such a harmonic function. If this harmonic function is really defined on all of the disk, okay, all of the disk, then there's only one choice for me, which is a constant function, which is a trivial function, okay, which is a trivial function. So, if I can accept, so again, if I strictly require that this function is harmonic everywhere, okay, including the original point, then there's one possibility for me, which is, okay, forget this log part, constant function. Otherwise, if I'm able to accept a singularity at the original point, then I'm going to have the log part, C1 log r. Okay. Again, is this a harmonic function? This is a harmonic function, but this is a harmonic function on the whole plane, excluding the original point. Okay, excluding the original point. Okay, so this is the so this is everything I would like to say. This is about the invariance in the 2 dimensions for the Laplacian and the rotationally invariant harmonic functions. Okay, and we'll be stopping here, and next time we'll pick up from the 3, the invariance of Laplace in 3. Thank you very much, and I will be in my office for any questions.
Yeah.